conquer approach. Part A, insertion sort. 8.1, insertion operation. So we will learn new sorting algorithm. The same sorting problem, so we need to consider a new solution. There is some reason, every time we improve, we try to improve, for some special aspects. All right, so here, the strategy. So we solve in a different way, different view. Strategy. Start with a simple case. So where we start, let's consider the problem with very small sizes. So then we gradually increase the problem size. All right, so here, every time we increase the size by 1. So you can treat it as an opposite direction for our problem size reduction. Remember, we took the problem size reduction approach in the previous module. Here, problem size increasing, just the opposite procedure. All right. How to connect two adjacent cases? You need to compare two adjacent cases. How much work we need to do? When you increase the problem size by 1, you need to do a little more work. All right. Let us work on the problem size. Let's draw some diagram. We try to understand it visually. All right. Intuition. When we start, our problem size is 1. So we have a 1-element array like this. Only 1 element. It is ordered, right? 1-element array, it is already ordered. We do not need to do anything here, right? When we start. Now, we want to increase the problem size by 1. A new element comes in, A1, that's a new element. So we want to make this new element join our old data, our existing, current data. Array, it's an array. Although 1 element, but we treat it as an array. So the new element should join the existing array. And as a result, the new array should be also ordered. So we want to insert A1 element into an ordered array. It is ordered. After the insertion, the new array should also be ordered. Look at this understanding. That's different from several of our understanding before, right? We didn't do it in this way. This is our new view. Okay, insertion view. All right. Then, we only need to do one comparison. We can determine where to place A1 element. Before A0 or after A0. One comparison is enough to make that decision. To make this new array order. Only one comparison. That's very simple, right? After that, we continue. Because our current problem size is 2, the next round, we want to increase the problem size to 3 by adding a new element A2. Look at that. But here, before you do new insertion work, this A0, A1 element in the array, it is ordered. So now you need to insert A2 in an ordered array and do some work, comparison. All right, now, how many comparisons do you need to put A2 in place? But here, we want to consider worst case, right? Worst case. Worst case, you need to do all the possible comparisons. Okay? Yeah. Okay. All right. Keep doing this. All right? Yeah. Because every time we add a new element into the array, after a certain number of comparisons, we make the new array order, and we move to the next step until we reach this general step. We want to insert a k element into the existing ordered array. Also ordered. Okay? Ordered. When you insert a k, you can make good prediction, right? Because the whole array is ordered. You can make good prediction. Okay? The order information is useful. If it's not ordered, then it's hard. So that information is useful. Order information is very useful. All right. Add a new element to the currently sorted array and then make it sorted. That's the work we need to do every time when we add a new element in an ordered array with a certain number of comparisons. Okay? Yeah. So with this understanding, you're pretty much there to have this new sorting algorithm. Pretty much there, right? You keep doing this until you process all the elements. Then you're done. Think about that. The procedure. Not very complicated. All right. Yeah. So observation. Insert an element in a sorted array at the right position. Okay. Yeah. So here you can see the most important operation is this insertion operation. So we need to study this insertion operation. All right. Let's look at the details of this insertion operation. Here there is another important part of work, shift elements work you need to do when you consider the insertion operation. Here, let me use another diagram to show you how to manipulate the elements in an ordered array to get a new element in place in the currently sorted array. All right. Now, we want to insert AK in an ordered array. We need to find a location, right? We need to find a vacant location for this new element. Find a room for AK. Okay? Yeah. But currently all the rooms are occupied, right? So you need to do some work to find the appropriate room for AK. Here, by shift operation. Shift operation. Okay, fine. here let us assume because when we have this array, let us assume we have plenty of rooms in this array. Plenty of empty rooms in this array. Array size is sufficient. All right. Before we insert AK element, before that step, first we need to find empty room at the end. Empty location. Actually, you can also imagine you lift. Originally, AK is here, right? AK is in the last place, location, all right? Now, but you lift it in a temporary location. AK, we want to move it to the right position, so we raise it, put it in a temporary location first. Temporary location, okay, all right. Then, in temporary location, that means this room is empty, okay? This room is empty. We can move another element into this empty room. Then we do comparison with AK minus 1. If AK minus 1 is greater than AK, then we shift AK minus 1 to its right hand side, right room, next door. Yeah. Okay, shift it. One shift operation to the next door. All right, yeah. Right. After that, then this room should be empty, right? Yeah. So we do another comparison, AK minus 2 with AK. If AK minus 2 is greater than AK, then we shift AK minus 2 to its right position. One position to the right. And then make original AK minus 2 room empty. And so on. Okay, all right. Then, sooner or later, at some appropriate location, here, after you shift I plus 1, this element, one position to the right. So you can imagine this room is empty. Okay? Then, when you compare AK with AK minus 1, you notice that AK greater or equal to AI. Okay? Greater or equal to. That means we should place AK after AI, not before AI, after AI. So that's this location. Yeah, that's this location. Yeah, this bottom empty location. Okay? Yeah. Now, finally, we find the right place for a K element to be inserted. That's all the detail, all the details. For one insertion operation, we need to do this much work. Very intuitive. So with this diagram, so you have a whole picture in your mind, so you can understand, the reason we need to do all these comparisons because we want to make room for this element. Yeah. All right. Any question? Yeah. Pretty straightforward. Not just comparison. Okay? Other than the comparison operations, you also need to consider shift operation. All right? Yeah. Shift operation, basically you copy one element to another location. Okay, assignment operation. All right. Yeah, but even that, we still treat comparison as the basic operation. Okay? You still treat comparison as the basic operation. All right. After this insertion step, you can see we can complete the whole sorting, right? If you run this insertion operation all the way to the end, you sort the given array. So we call this method insertion sort. Insertion sort, a new sorting algorithm. Okay? Yeah. All right. Here you can see the number of assignment operations or the number of comparisons. Both. We can use big theta of k for each insertion step. Worst case and average case also. Average case, approximately 1/2 of k. Worst case, how many comparisons? Worst case. Precisely k minus 1 comparisons. Yeah, but approximately k. Approximately k comparisons. All right. Next, 8.2, implementation of insertion sort. Actually, here, for the implementation, pretty straightforward. We just run for loop. And each iteration, we do one insertion operation. That's the implementation. All right. Compare and shift operation. All right. Like this. Compare and shift operation. Because every time when you do one comparison, there is a possible shift. Possible shift. Okay? Very close to 1-to-1 ratio. But you can argue if AK is the largest, then you do not need to do assignment, right? That's true. If AK is the largest, you do not need to lift it. You can keep it there. So you can adjust your implementation a little bit. You do comparison first. How about that? You do comparison AK with AK minus 1. If AK is greater or equal to AK minus 1, do nothing. Do nothing. Insertion is done. Don't do insertion. Right? Only when AK is less than AK minus 1. Then you copy it to the temporary location and make the assignment. And copy it and do the next round comparison. So you can adjust your implementation slightly to improve a little bit. Improvement is quite small, but we still, if it's possible, we want to do the improvement. All right. Worst case analysis. For the worst case, you need to do comparison from beginning to end. Okay? For each insertion operation, you do comparison from beginning to end. Okay? Yeah. All right. So one element, when you insert new element into one element order array, you need one comparison. Two element array, worst case, two comparisons, and so on. The last insertion, inserted into an n-1 element ordered array, you need also this many comparisons for the worst case. So the worst case efficiency, adding these numbers up, you get 1/2 times n times n minus. Standard formula. Okay. So you can see in this way, that's the worst case efficiency. What is the best case efficiency? Best case. Also interesting, we want to look at it. This worst case is the big theta of n squared. Growth function, if you ask the growth function, we ignore 1/2, right? We look at the leading term. So we ignore -1 term. So only n squared we want to use for its growth function, big theta of n squared. All right. Next, best case efficiency. Every time in each insertion operation, you only consider the best case. How many comparisons you need to do for the best case? Each insertion, you only do one comparison. AK with AK -1, the best you can have, AK is greater or equal to AK -1. So then you're done. One comparison in order, already in order, so you can move to the next possible insertion. All right? Yeah. Still, one comparison, move to the next iteration, and so on. Okay? So you add up all these one comparison insertion step, adding up n -1. So the asymptotic notation, the growth function, big theta of n. Now you compare worst case, best case. How much is the difference? N squared, very slow, but the best case, n, very fast. That's the main property of this insertion sort. Insertion, each sorting algorithm has some properties. So this one, the best case, very fast. This is the most prominent property of the insertion sort. Okay? Why I say most prominent? Because later, when you look at other sorting algorithms, we won't have this property anymore. Okay? Only insertion sort has this property. Okay? Best case in this big theta of n category. Okay? Later, if you look at other sorting algorithm, the best case you cannot have this good efficiency. So most prominent property of insertion sort. That could be useful. Yeah. This property could be useful. Okay? Yeah. So, if you're learning insertion sort, you have to know this property. Okay? This property. All right. Average case, each insertion operation, you can consider the average case. Now you're adding up, still big theta of n squared. It is approximately 1/2 of the worst case. Yeah, because the normal comparisons spread in a linear way. So here we do not do that detailed work. Approximate 1/2 of the worst case. That 1/2 is just constant. So we have this big theta of n squared. efficiency class. Okay, got it. All right, we complete insertion sort. So you can see the sorting algorithm is very simple. That's the whole story of the insertion sort. Okay, all right. Yeah, how to derive? Yeah, so it's not hard. It's quite straightforward. You can do it as a practice, but here I do not. I do not need to do this. It's quite simple. Conclusion. Because this insertion sort has a very special property. So that property, although not big, it's not a big one. Okay? That means the chance you use that property is not very big. But when you have a situation, here I describe the situation. When you have appropriate situation, you need to know you can apply this special sorting algorithm. So what is the situation? Here, let me describe. The data given is almost sorted. When you have this situation, insertion sort is the best. Yeah. So, this is something useful we learned from this new sorting algorithm. All right. If I draw a diagram, describe our data property. The given data has this property. Almost sorted. What do you mean almost sorted? The whole array is almost sorted only at these a few scattered locations. Small places, scattered locations, it is not sorted, not ordered. If your data has this property, okay, if you apply other sorting algorithm, then you need to do, from beginning to end, the same amount of work as usual, but for insertion sort. Because you only need to do the work at these locations, right? For other places with ordered elements, one comparison you're done. Okay, think about that. One comparison, you move to the next one. That's the best, right? Yeah. So then you should apply the insertion sort. Because if you apply the insertion sort, you can get a big data of n efficiency. The best you can get. Okay? For other sorting algorithm, the best you can get, even for the best case. Okay? Even for the best case, the best you can get, big data of n log n. Okay? That's the best you can get. Okay? Even the quick sort. Yeah, we will quick sort in this model. Quick sort, usually it has the fastest overall efficiency. Okay? Even quick sort, the best case, still big O of n log n. Not as good as this insertion sort. Okay? Yeah. But you need to check the condition. Alright? Check the condition. This could happen in some real world applications. This could happen. Alright. So that's what you need to know after you learn the insertion sort. Okay, not too much. All right. Next, let me do some simple example, but related to the insertion sort. 8.3 example. Sort 4-element array. Sorting 3-element array. We did in one quiz, right? Remember, in one of the quizzes, I gave you that problem sorting 3-element array. 3 comparisons for the worst case. Now we need to look at this question. We want to sort a 4-element array for the worst case. Okay. Related to the insertion sort, but we need to modify it a little bit. Okay. Because if you apply insertion sort directly, you won't get the best solution. You can try. Okay. Let's try if we want to apply insertion sort directly. How many comparisons you need for the worst case? Let's do it. So the standard insertion sort. Okay. All right. A0, okay, A1, that's one comparison, right? The first comparison, okay? Then, actually we did that, right? We do not have to do it this way, but because it's simple, let us do it this way, okay? A2, 2 more, right? 2 more comparison for the worst case, remember? Okay? A3, 3 more for the worst case. 1 plus 2 plus 3, 6 comparisons. If you apply the insertion sort directly, solving this problem, your answer will be 6 comparisons. It's not the best solution. It is not the best solution. We can do better than this one. We can do better than this. Not. But we can modify our inversion operation. Modify it. Now, let's look at improvement. All right. Improvement for the first 2 rounds. It's fine. For the first 2 rounds, that's too simple. How much improvement in the first 2 rounds? In the 3rd round, we have some improvement. 3rd round, we do some improvement. Okay. 3rd round, we already have an ordered array. A0, A1, A2 in ascending order. Okay. Now, our question. We want to insert A3 into the currently ordered array with the minimum number of comparisons. Any idea? Observe the property of our data. Our data has that property. When you look at that, what special property you can find to make our insertion operation as fast as possible?
You compare the middle, you can
Correct. Binary search. How do you do binary search? Compare the one in the middle, right? Why you compare the one at the end, right? You can compare the one in the middle. Okay? Think about that. You can compare the one in the middle. Then, either greater or less than. If it's less than, one more, right? One more. If greater than, also one more, right? Total, two more. How about that? Two more, not three more. Okay? The older way, we need to do three more comparisons in the third line. But the new improvement method, only two more comparisons. So the final answer, 1 plus 2 plus 2, we get 5 comparisons. The best solution for this case is 5 comparisons. How about that? How about that? Okay. Binary search idea, we haven't learned yet. We will learn later. We will learn binary search in more details. But everyone knows the binary search, right? We can apply that idea to the one in the middle. Alright. The next question. Now, here we notice if we compare the elements in the middle, applying the binary search idea, we can do faster. Then some of you may ask question, when we do the standard insertion, so can we take this way? Standard insertion? No. Let's revisit our insertion source solution. We compare the element at the end. We always compare element from the end. There is interesting thinking. You may want to try to compare in the middle. Unfortunately, the answer is you cannot do that. You cannot do that. Although, if you can do the comparison in that way, but it won't improve much. The reason is, remember the shift operation, right? Even you find the right location, but you don't have room for it, right? You can find the right location faster by the binary search, quickly. But how do you find the room for the element, right? You need to move, shift to the right one by one. So you still you cannot move much. Think about that. You cannot improve much. Okay? Because of the shift operation. Here, we don't worry about shift operation, right? Because we have small number of elements, we do not even need to use array. We can use variables directly. So we do not need to worry about the shift operation. So that's the reason we can say. So when you need to consider shift operation, then you cannot say from the binaries. So that's one thing. Second thing. Can we expand this idea to 5-element case here? We want to sort. 5-element array. Okay. Can we generalize? Because from 3 to 4, we did it successfully. 3 to 4, we did it successfully. Here, can we improve? Here we have 4 elements. 4. You can assume we already have 4 elements: A0, A1, A2, A3. 4 elements sorted in 5 comparisons. Okay? In 5 comparisons. When we sort 5-element array, how about we sort the first 4 elements in 5 comparisons? Right? Then, let's consider the last element in 4. We want to do insertion operation. And you can apply the binary search. But when you apply the binary search, for the worst case, how many more comparisons do you need for the worst case? More. Just only more. You need binary search. 3 more, right? 3 more, right? Right? Because you can compare either x1 or x2. Same. Okay? But when you compare x1, you need to consider A4 greater than A1 case. Because smaller, that will be easier. So here we want to focus on the worst case. We want to focus on the worst case. So worst case, it should be A4 greater than A1. Then you need to consider A2, A3. That means you need 2 more, right? Even with binary search, you need 2 more comparisons. So total for this A4 element to be inserted, you need 3 more comparisons. Okay? Yeah. So the total 5 plus 3 equals 8 comparisons. All right. Is it the best solution? Is it the best solution? 8 comparisons? Do you still remember? I gave you how many comparisons you need to sort 5-element array before. Remember in one class before, I talked about finding the median of 5 elements and the sort 5 elements. Those 2 problems. I give you 2 numbers for the best solution. I told you it's very challenging. Those 2 questions, very challenging. Any of you here still remember I gave you those 2 questions before. Very challenging. And then the numbers I also give you. Okay, Lloyd? All right. 7 comparisons. All right. So then let's repeat. Okay. Finding the median of 5. 2 questions I gave you before. Solving this one. Finding the median of 5. The best answer, 6 comparisons. Okay? All right. Second question. sorting 5-element array, 7 comparisons. One better than this one. That means if you do not make some smart move, right? You only do this straightforward insertion, you may not get the best solution. Even you apply the binary search. We know the binary search is very good. We like it. Yeah. But here the question, you can see when you have 4 elements, this structure, so even the binary search, because you need to do 3 comparisons to get it inserted. That's not efficient. That's not efficient. Okay. Yeah. So here, you have to find a way, more sophisticated way, not the simple way, more sophisticated way. You can get a 7 comparison solution. Very challenging, but after midterm, I can find time to talk about these 2 solutions. These 2 solutions are related. The first half, the same. Second half, they are different. First half, that means the first 3 comparisons, the same, exactly the same. First 3 comparisons, very simple. They're exactly the same. Then after that, then the way we handle them different. Yeah. All right. Yeah. So here I also want to leave some time for homework questions. Tomorrow is the deadline, right? After extension. Tomorrow is the deadline. So if you still have a few questions, then I can answer a few more questions here. Okay? Now let me know what's your questions. We have about 20 minutes, so I can answer those questions. Let me bring up the question sheet and project it on screen so I can talk about it. This time, I will enlarge it, okay? To make you see better, enlarge it. Yeah. That's the maximum I can do. Yeah. Zoom plus sign, maximum. Yeah. But you have your, sheet if you need. Look at your own paper. Which one you feel relatively hard, so you need me to explain a little bit. One thing, question number 13, let me make a few comments. Because I noticed some students use the graphic calculator, some software, don't do that, all right? Yeah. One student showed me using the graphic calculator, the output is ridiculous, okay? The reason is simple, because here, the function I gave you, the amount of computation is out of the scope of the software, okay? The software cannot draw the graph reasonable well, because it's out of the scope. It cannot handle, okay? Because the function is so big, move far away into the universe, right? Far away into the universe. So the software cannot present the graph well. So it will output ridiculous, some simple, I saw it. Once they showed me that. Don't do it that way. Use our, we did in class. Use our result in class. Module 2 examples. Remember part B. Module 2 part B. We did a few examples using that part. Okay, alright. So that's the comment for this question. Any other questions you'd like me to explain a little bit? Number 14. Let me just say a few more words. Number 14. Number 14. First, it's a simple question. I believe most of you can get it easily. But why I mentioned that? Remember here, I just mentioned that finding the median of 5 question. This step is part of that finding the median of 5 step. Yeah. After first 3 comparisons. Here, remember the result I give you here. A1, x1 less than x3 less than x4, and x1 less than x2. That's what you can get after first 3 comparisons. Okay? After the first 3 comparisons, then before you do more comparisons, eliminate, based on the given information, which element cannot be the median. Look at that. You can eliminate one element from consideration for the median. After you do that, the array size becomes 4. Alright? Array size becomes 4. Okay? Yeah. Then you find the median, how to do it, find the median. Another related question I also gave you here. Another related question here. Let me find it. This one, question number 23. Okay? Question number 23. Second largest. Also. Because second largest and second smallest. The same. Okay? It's not too hard. So then you use this question, this solution, you can find a median of 5. See? See? If you want to try, but here, these 2 questions. These 2, second largest. First, you need to know the largest, right? In order to find second largest, you need to know the largest. What is the largest? Question.
Give my answer for what I thought the largest would be, or what would either be x2 or x4.
Yes. X to x4. You do one comparison, you get largest. After that, then second largest. Second largest. Okay? Not too hard. Not too hard. Yeah. So I do not want to, yeah. All right. So other information you would like me to talk about? Other questions you would like me to talk about it? Oh, number 16. You need to find the value. Yeah. The reason, based on my grading, too many students couldn't do this one. Okay? Too many students couldn't do this one. Do calculation. Okay? So this one, do not apply our existing result. These 2, you need to do calculation. Compare 2 numbers. Okay? Do not directly apply our existing results. Okay? All right. Other questions? Question 10. Oh, no, you asked me one question.
No, 10 is good.
Yeah, because question 10, a few students asked me that, so I make some comments. And here, you look at the number exponent numbers 3, 7, 11, 15. All right. So the first observation, remember common factor. When we work on the Horner's rule, remember our basic step, factorize the common factor, x cubed common factor. Okay? After that, inside another polynomial, right? Another polynomial, you can relate it to the structure, to the first question. First question, x squared, x to the fourth, x to the sixth. But that one, after factorization, what do you have inside the parenthesis? X to the fourth, x to the eighth, x to the 12th. Right? Similar structure. All right. Yeah. So that's the first observation. Also, another principle in your mind when you solve this problem. Try your best to reuse your resource. Remember the idea of reuse the resource. So what do you mean reuse the resource here? Let me use this. Okay. When you do computation, you save the intermediate result. Okay? When you do computation, you save intermediate result. What do I mean then? Let me give you an example. Okay. X times x equals x squared. All right? So that is, you spend one comparison, you get a value of x squared. Okay? This x squared we treat it as an intermediate result. You save it, don't throw it away. Okay? Because the storage space is very cheap. We know in current computer, storage space very cheap. So we can afford, so we save it. Save it. You will use one variable, temporary variable, we save it to be reused later. Okay? Yeah. Then reuse as much as you can. What I mean, so when you calculate x to the fourth, x squared times x squared equals x to the fourth. Just one more multiplication. Because, question?
Your writing's not showing up on screen.
Oh, sorry. Yeah. All right. Yeah. My writing. Oh, sorry. Yeah, it's here. All right. Sorry. Yeah. When you go back, you can. Yeah, sorry. Yeah. We didn't miss much. Yeah, thank you. Yeah. All right. Yeah. Okay. Sorry. I forgot. Yeah, remind me as soon as possible. Yeah. All right. Yeah. X squared times x squared, reuse this x squared resource. All right. One more multiplication, you get it. Then another one, reuse. Okay. What's that? Well, because you need to calculate x cubed, right? You factor x cubed out. You need to use x cubed value. That means x squared times x equals x cubed. Just one more comparison. Because x squared, you can grab it directly. Do not calculate it. You save it. You just reuse that number. Good? Yeah. So that's for that question number 10. Try to explore this. Reuse the resource idea. Try to push it as hard as you can, this idea. Okay? Reusable. Resource reusable. Alright? That idea. Okay? That's question number 10. Next question. Try to ask me, let me bring up the question. Edward?
For number 6, does brute force count as an algorithm?
Number 6, yeah, good question. Brute force, yeah. Finding minimum, all right, yeah, here. Number 6. Actually, we have the solution, right? In our class, we have the optimal solution, right? Finding the minimum, n minus 1. N minus 1, is it in this class? Is n minus 1 belongs to this class? Because minus 1, minor term, we can ignore, right? Okay. Just thinking that way, all right? We have the solution. Here I ask you, is it possible? Because you just connect to that known solution. And you check it. If our known solution belongs to this category. That's simple. Okay? That's simple.
I know you talked about it before, but can you talk about number 20 again?
Number can be. Oh, yeah, I did. I only mentioned you need to know our formula, right? Yeah. So here I remember the formula, the number of moves, m1 equals 2 to the n1 minus 1. n2 equals 2 to the n2 minus 1. These two formulas, right? Yeah. Adding up, yeah. m1 plus n2 equals 134. All right. With this information, can you find a way to figure out n1, n2? Not too hard. Not too hard. Yeah. Question.
Can you show the pointer?
Oh, I always. Sorry, I always forget that. All right. Here, this part. Yeah, sorry. Yeah. Yeah. See? Yeah. Because, these two formulas. All right. Yeah, hopefully not too hard for you. Yeah. I think we can have one more question. We have 5 minutes. One more question. Oh, 21. Yeah. I hope I can. I do not need to. I'm telling you. Yeah. This one, yeah. Actually, I gave hint before, right? Long time ago. Yeah. I can repeat a little bit. Yeah. Connect to that finding the minimum problem. 135 element array. If I ask you a question, how many comparisons you need to find the minimum? Can you tell me? Just finding the minimum. Yeah, n minus 1. All right? Here. Is the minimum belongs to the bottom 5, among bottom 5, the minimum number? Right? Okay, yeah. So that's not the best solution. So that means you have a solution so your solution should not be worse than 134 comparison. Your solution should only be better than 134. Okay? Because now you don't have to find the very minimum, smallest one. When you reach close to the bottom, you can stop. You can stop earlier before you reach the bottom. Because finding the minimum, you reach the bottom, right? You do the comparison, really get to the bottom. Here, bottom 5, can you stop earlier? Not necessary to the bottom. When you close to the bottom, can you stop? When you're near the bottom, can you stop? Because you only need to make sure among bottom 5. When you're in the range among bottom 5, you can stop. Think about that logic. You're very close to the bottom. Okay, do you have some room? Yep. So you want to save some comparisons. So you do not need to overdo it, right? When you reach the bottom, you overdo it. So stop earlier when you're in the range of bottom 5. Think about that. When you are in the range of bottom 5, you can stop. How about that? Yeah. How about that? Interesting idea. All right. Yeah, I think we pretty much we run out of time. Yeah.